7.1 We are instructed to give a definition of base in terms of the Arrhenius theory. Arrhenius theory tells us that base releases hydroxide ion in water or solution, or you may say, base forms hydroxide ion in aqueous solution. For further more understanding, let us little bit talk about acid as far as Arrhenius theory is concerned, although we are instructed to define only base. As for acid, Arrhenius theory tells us that acid releases H+ ions in aqueous solution. On 7.2, we have to explain how a weak base differs from a strong base. Well, what you must really know about strong bases, they dissociate complete in a aqueous solution, which means that all that start up strong base will turn into ions that even if you check in that aqueous solution, you find that no more strong base left, only ions or conjugates are present. And as for weak bases, they turn to partially dissociate in solution. That means if you run some checkup test in that solution, you can find that even though there are ions, but there is still that weak base present in that aqueous solution. So, summing it all up, we say, strong base dissociates completely while weak base dissociates incomplete. That is expected answer for 7.2. We are given this substance NaHCO3, which is named sodium bicarbonate. It is baking soda. The instruction given is to write the balance equation for the hydrolysis of this sodium bicarbonate. Let us first understand the meaning of the word hydrolysis. In simple explanation, it is a chemical decomposition or breakdown of a compound due to reaction with water. So, this prefix means water, and this suffix means to break, therefore this means, we break down sodium bicarbonate into smaller molecules, but firstly you must know that this substance is made up from reaction of H2CO3, a weak acid, and NaOH, a strong base. So, sodium bicarbonate is breaking down into Na+ and hydrogen carbonate. Na+ is a conjugate of strong base, and hydrogen carbonate is a conjugate of weak acid. Therefore we take conjugate of weak substance, which is this hydrogen carbonate, we react it with water, which forms carbonic acid, and hydroxide ion. Note, the presence of this hydroxide ions means the solution is basic, even though there is that acid, that doesn't change anything. So, this chemical reaction is the one required on 7.3. Now on 7.4, there is this information given, reads as follows. A learner wishes to identify element X in the hydrogen carbonate XHCO3. To do this, she dissolves 0.4 grams of XHCO3 in 100 cm³ of water. She then titrates all of this solution with 0.2 moles per decimeter cube of hydrochloric acid solution. Methyl orange is used as the indicator during the titration. And on 7.4.1, we are requested to calculate the pH of the hydrochloric acid solution. The pH is calculated from this formulas. But we gonna use this one on this problem because this one will need us to have the value of pOH, which we don't have now. So, in that case we shift to this one which fits here. On this hydronium ions, we put the concentration of hydrochloric acid given. Then, calculating all this, we get pH to be 0.699. This is the answer for 7.4.1. Now, there is an additional information, it reads as follows. At the end point she finds that 20 cm³ of the acid neutralized all the hydrogen carbonate solution. This is a balanced equation given for the reaction. Then, furthermore we must identify this element X by means of a calculation. Let us convert this 20 cm³ to be in decimeter cube because this concentration of hydrochloric acid is in mole per decimeter cube. So, we simply divide this 20 by 1000, then the number we get, it is 20 times 10⁻³ decimeter cube. So, to get to know the element X, we have to know its molar mass. To do that, we say molar mass of XHCO3 equals molar mass of element X plus molar mass of this hydrogen carbonate. Remember what we did here, but here it is not that Na+. We are here to find out. We take the concentration of HCl given converted into moles and to molar mass. We use this formula for concentration. We substitute like so. This is the HCl concentration and this is that volume we converted recently. We get mole of HCl to be 0.004 moles. Then, we use the mole ratio to get moles of XHCO3. Because on here, the mole ratio is 1:1, which mean moles of XHCO3 equals moles of HCl as we are using stoichiometry. Then, we use this formula to get molar mass of this substance as we are given its mass. We substitute as so. This number is the moles we got recently, and this number is this mass of XHCO3 given. This give us the molar mass of XHCO3 to be 100 grams per mole. Now we have molar mass for this substance, let us know this one. We add molar mass of each element together on this hydrogen carbonate using period table, like so. We get its molar mass to be 61 grams per mole. As it is so, we take these both molar masses to substitute on this equation as so. By so doing, we get molar mass for element X to be 39 grams per mole. Then, take this 39 to a period table to see which is that element we were looking for. That element seems to be potassium. As now we know element X is potassium, which mean this substance in full will be potassium bicarbonate. If you like such educational video, please subscribe for notification of new posted videos as we post a new videos every week.